Okay, so here we are again. We're going to talk about periodic properties. As I mentioned early on in the development of the periodic table, people like Mendeleev were noticing that similar properties were occurring, and that's how they grouped the elements and uh, decided how the periodic table would be arranged. They arranged them so that the columns represented elements that had similar properties, and we're going to talk about uh, some trends in the element on the periodic table. Okay, so let's see. One trend that we should get a handle on is size. So if I look at lithium and potassium, they're two elements that are in the same group. So they're both alkali metals. Lithium is way up there near the top, and potassium is, well, lower down in that group. So lithium is in the second shell, potassium is in the fourth shell. So if I'm looking at how to compare their sizes, their sizes are going to differ according to the shell. So lithium only has two shells of electrons, potassium has four shells of electrons. So potassium is obviously bigger because it's got more shells. So which has the largest atomic radius? So within the same period, so lithium is in the second period and so is fluorine. They're in the same period, different groups. So which would you expect to be larger? Okay, this is always counterintuitive. This kind of, you make that little just take your hand and make the sound on your forehead. Um, Fluorine has a greater atomic number than lithium, so you might expect a bigger atomic number, bigger atom. It has a greater mass, but in terms of its girth, it is smaller. And the reason primarily is that if I look down in the nucleus, I've got a +3 charge down in the middle of lithium. I've got a +9 charge down in the middle of fluorine. The greater positive charge is going to draw those electrons in more. So with more nuclear charge, the electrons are attracted more strongly, so the atom is smaller within a given period. Okay, so if I'm looking at the trends, and I always tell students to scribble these arrows in on the periodic table that I hand out with the exam, so that the size increases as I go to the left, and it also increases as I go down. So remember I said lithium was bigger than fluorine, and potassium was bigger than lithium. So the size trend is to the left and down. There are some other size trends. So if I'm comparing any atom, in this case potassium, with its positive ion, so if I steal an electron away from potassium, then I'm going to have one fewer electrons than protons. So that means I have more positive charge than I have negative charge. So if I'm looking at the electron arrangement for potassium, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. When I take an electron away, I always take out the outermost electron. That's going to be the easiest one to grab. And if I grab that fourth shell electron away, that's going to leave me with just three shells of electrons. So taking an electron away will make an atom smaller. And technically, once I've taken that electron away, this is something that we call an ion. And if it's a positive ion, it is called a cation. So even though you've learned in elementary school that TION is shun, this T here gets a hard T. It's a cation. Okay, we can go the opposite way. We can add electrons to an atom. So if I add electrons, taking electrons away made it smaller. Adding electrons, logically seems like it should make it larger. And it does. And the reason isn't necessarily that we will go beyond the shell up to another shell, but what's going on here in this case is that adding an electron will add repulsions, and those electrons repel one another more, and we will end up with a bigger entity. So in this case, I've got a negative ion that's been created by adding an electron. And a negative ion is called an anion. The terms anion and cation come from where they would form if we were doing an electrolysis experiment. They happen at the anodes and cathodes and things like that. Okay, so ionization energy. So I'm looking at taking an outermost electron away from an element, and I have to consider whether it's more difficult to grab an electron from lithium or more difficult to grab away from potassium. And this all has to do with size. So it's going to take more energy to remove an electron from closer to the nucleus. So the electron that I'm taking away from lithium is going to be much closer to the nucleus than the electron that I'd be taking away from potassium, which is way far away from the nucleus. So potassium he's so fat he doesn't even hardly know that he has that electron out there. Okay. So let's see, when we look within a period, so when I compare lithium and fluorine, which are in the same row of the periodic table, there's a couple of factors to consider. It's both size, so taking an electron from close to the nucleus is going to be more difficult than taking an electron far away from the nucleus. And also, I've got a greater nuclear charge, so I'm pulling that electron, and on the other end of that is a positive 9 charge. Here I'm only pulling against a positive 3 charge, so it's going to be much more difficult to pull an electron from a positive 9 charge, especially if it's a small atom like fluorine. So it's very difficult to pull an electron away from fluorine. Okay, so when we're looking at ionization energy, taking that first electron away, the trend is that the ionization energy increases up a group and to the right across a period. So elements that are very difficult to take electrons away are going to be up in this corner of the table. Elements that are very easy to take electrons away are going to be down in this corner of the table. So these are where we form positive ions, and we'll later learn that all of our metals pretty much are very good at losing electrons, so these tend to be our electron losers. And then over here in this corner of the table, except for the noble gases, they don't like to, they've got the perfect arrangement of electrons, but these elements up in this corner tend to like to gain electrons.